Okay, guys, so I'm Tim, and I'm going to be covering the topic of ACI and really its operational benefit to the data center in the next 75 minutes or so. All right, a little bit about me. I've been a Cisco engineer almost 20 years. I started in routing and switching, and then moved into optical and then voice, and I've been doing data center for the past 10 years. That includes Nexus, all of Nexus, UCS, server virtualization, security, physical infrastructure, you name it, data center focused, data center architect, with a focus on Cisco technologies, but not exclusively limited to Cisco. So the data center is a pretty exciting place, in my opinion. It's where a lot of technologies have been converging, and we may take it for granted, but things like server virtualization, right? VMware, think about how revolutionary that is to be able to install multiple operating systems on the same physical server and then move those virtual machines around within the environment. We kind of assume that that's what a data center is supposed to do, but it wasn't very long ago that we had one application per operating system and one operating system per server. So we've come a long way just with that technology, let alone storage and security and intelligence. And that's really what ACI is about. It's about an intelligent infrastructure, an infrastructure that can guarantee service and security to an application no matter where it is on the ACI fabric. Now this all began, you guys, with something called software-defined networking, or SDN. You've probably heard this buzzword thrown around. It is somewhat ambiguous. I hope to clarify it to some degree, enough to set the stage as to why Cisco's application-centric infrastructure, or ACI, is unique in the market, different from a lot of other offerings that you may find from Juniper or VMware or Arista. So we're going to talk about SDN. We're going to talk about the place of VXLAN, which is a new open standard within ACI. It's a tunneling protocol, for those of you who don't know. We'll talk a little bit about the tenant and policy model, and then how ACI integrates with hypervisors, that's server virtualization, as well as firewalls, load balancers, and WAS appliances. That's what Layer 4-7 means. Talk a little bit about architecture and migration, a tiny bit about automation and troubleshooting, and at any time, if you've got questions, I want you to interrupt, okay? But really, take this as an opportunity to learn as much as you can. I've already invested in ACI, clearly, and clearly training is the mandate, because there is a learning curve associated with ACI. It is a radically different approach. It does not mean that our skill sets are void. In fact, you can't really understand and appreciate ACI unless you have the kind of routing and switching background that most of you probably do in a traditional sense. But what ACI has added to that picture is an incredible amount of monitoring and automation. All right, now folks, this is my whiteboard. I want to make sure you all can see it. Okay, it's blank currently. But I'm going to draw a little picture here of just a standard infrastructure. Let's say maybe it's a 3-tier infrastructure where you have a core layer, an aggregation layer, and an access layer. And our core and aggregation layer is fully redundant. And then we usually have links like this down to our access layer, right? And this is a traditional 3-tier data center design. Now, in most cases, up until very recently, every single one of these infrastructure devices, switches/routers, usually these are multi-layer switches, they will have an operating system which is full stack. Full stack means that all of the capabilities, all of the functions are actually built in locally into the operating system that runs on the device. So if you want to add, let's say, some type of routing protocol support, the vendor has to actually write it into the operating system code. Let's say it's iOS or NXOS, right? And then that's locked, right? There's no ability for you to go in with a software developer's kit and embellish or add functionality to Cisco iOS, right? That's just not what Cisco or any other vendor in their right mind would do, okay? They don't open up these these are not open source platforms. They're closed, okay? Even if there are open APIs, the operating system is closed. So this presents an issue in terms of the kind of delays that we experience because we have to wait for vendors to support features. We can't experiment on our own. And it requires a great amount of hardware resource on each one of these devices for housing the operating system, being able to run it in real time, have enough memory for the tables and the databases and all of the processes and sub-processes that are running on any given system, right? You've got things like spanning tree and BPDUs and UDLD and VTP and LLDP and CDP and all sorts of layer 2 processes running in the background, let alone any other user-initiated processes that you might turn on, right? And then there's the operating system itself, which has daemons that are running. So it's a pretty heavy-duty mandate to actually run an operating system on a piece of equipment and then also have it pass frames or packets. So the SDN model, you guys, is different in the sense that instead of actually having an operating system, a full functioning operating system with a full stack on a piece of equipment, we install this thin, bare bones, I wouldn't even call it an operating system. It's basically enough to power on the box, run tests on the hardware, and then open it up to the programming of flow tables from an external device known as a controller. So the controller actually has the big picture of the environment. The controller has what we call the master route forwarding database, as well as any other like MAC address table databases. And then it uses a protocol called OpenFlow to write the decisions that it's made in its master databases to each of the local devices. So there are what we call flow tables on those devices, which are hardware CAMs that store decisions in terms of what to do with packets. So when a packet comes in on that switch, it knows what to do with that packet, where to send it next. But it doesn't determine that flow table on its own. It's given that instruction from the controller. Now the benefit of this is that the controller, the master controller, really has insight and purview into the entire infrastructure and can make holistically based decisions. The downside is that the controller becomes a bottleneck. If the controller goes down, no more convergence or route table or MAC address table updates can actually take place until the controller is back online. Okay, we can avoid that through high availability and having a cluster of controllers for the most part. But it's still a bottleneck because each one of these devices is not actually running a routing protocol or even spanning tree or anything like that. It's a completely new paradigm. If you're interested, Google's entire worldwide data center infrastructure is actually run on this model, SDN. They go out and they buy their own boxes, they build their own hardware, and then they've custom designed their own controller, which uses OpenFlow to program these commodity switches. Now, obviously, there's reason for Cisco to not want to go to a totally open type of format, and they haven't. But there's actually some real merit behind their slightly different approach with ACI. Now, in terms of the physical infrastructure, and this is something that is changing across the board, so even if it's Cisco or other vendors, we are now moving to what's known as a two-tier spine and leaf model. And the benefit of this is that you can expand almost infinitely without having to actually design and deploy new switch blocks like we did in a traditional sense. So if you need more leaves, you just add them. Right? And if you need more spines, and if you need more bandwidth to support the leaves, you add more spines. I'm going to remove these 2 leaves. We don't need them right now. And you can guarantee that the distance between any endpoint that sits on a leaf connected to this fabric is only ever going to be a maximum of 3 hops away from any other device that sits on this fabric. So you have guaranteed reachability of 3 hops or less between any 2 endpoints sitting on the same fabric. That's just physical design. But the real distinction between this model that I was showing you earlier over here, where we had an external controller programming each of the infrastructure devices, and here, where we also have a controller called an APIC, Application Policy Infrastructure Controller, it's also going to program all of the devices. It is a central point of configuration. However, these Nexus switches run a version of operating system that's specific to ACI. It's not an X operating system. Although these devices can run an X operating system, by the way. They wouldn't be in an ACI environment if they were, but they do have the possibility of running what we call standalone NXOS mode. But if you're running the ACI code, it's still a fully functioning operating system, meaning these devices are going to run their own protocols between each other. But the APIC is going to be the master database for policy and configuration. So that means that you, as the network engineer or administrator, are going to log into this APIC. You're going to open up a GUI. You don't have to. You're not limited to just the GUI. There are other options. There's command line, and there are APIs that you can use with a RESTful client. But assuming you access the APIC the way most people initially do, you open up a web browser, you point to the IP address of the APIC, you log into it, and then the configuration changes you make are propagated out to the switches by the APIC. So you don't actually log into the individual switches. You log into the APIC to make changes to the fabric as a whole. More importantly, although the APIC is configuring and initiating processes on these switches, the switches themselves are running routing protocols, and they are converging their own database flow tables, their routing tables, their MAC address tables. In fact, there's a new set of tables in ACI called endpoint tables. So you get the benefit of SDN, but you don't get the bottleneck. And on top of all that, what's really, really important about ACI is this policy database. This is what allows us to guarantee serviceability. So if you promise your users a specific or a window of response time or performance, and in the traditional infrastructure, you would enforce that through things like QoS and access lists for security. In the ACI environment, we have these policies that will guarantee minimum and or set maximum amounts of bandwidth on applications, and will limit communication between the specific kinds of endpoint groups or users that we specify. So you get security built in, you get QoS built in, and you never have to go manually updating configurations in the fabric. So in this model, right, if you want to stand up a new service, the server team comes to the network team, they say, hey, we want to deploy a new application. You got to figure out a subnet that they're going to use. You got to let them know what that subnet is. Then you have to set up a VLAN, right? And you need to configure that VLAN on all the switches in that layer 2 domain. So let's say our layer 2 domain was the aggregation switches on down. In this case, it wouldn't be too much work. There'd only be 8 switches that you needed to create the VLAN on. But you'd still have to go in manually and create VLAN, whatever it is, VLAN 100, on every single one of those switches manually. And that just opens things up to human error. Also, if you wanted to guarantee service, you'd have to go amend your QoS policies. And when it comes to security, you'd have to go add to or remove entries from your access lists to support this new service on the network. All of that is prone to human error. All of that is manual today. Even if you're doing scripting somehow behind the scenes, it's pretty much a manual process. You have to connect to each one of those switches and push those configs into them, assuming they're correct. Here in ACI, you generate what's known as an application network profile. It defines the policy between specific sets of devices, and then the APIC configures the infrastructure on demand. So that means that when a leaf recognizes that a server has actually attached to it, then it downloads the policy from the APIC and enforces it locally on that leaf that that server or endpoint has now connected to. But prior to that, there's no need for the policy to be stored in the hardware tables of those leaves. So it's highly efficient. That's different than the older model where you have to have a full access list. Whether or not you've got devices that are attached to that leaf, you still, in most cases, have to build comprehensive access lists and deploy them everywhere. That's not the case with ACI. So, central point of configuration, network engineers define policies. Those policies are then enforced dynamically on the fabric, on demand, and the devices inside the fabric are actually still running their own route processes and layer 2 and layer 3 processes under the master control of the APIC. So it's a hybrid SDN solution, best of both worlds. Now these links in ACI between the leaves and the spines, these are 100 gig links. And I don't think I mentioned earlier that I've actually been working in production environments on ACI for almost 2 years, in addition to teaching ACI. And I'm currently a member of Cisco Advanced Services, and I am on a very, very large global project where we're deploying ACI in 55 data centers, 45,000 ports that are going to be running ACI. And it's a huge migration project that's going to take 2.5 to 3 years to complete. And initially we had 40 gig links between the leaves and the spines, but recently the new line cards on the spines support 100 gig. So you get 100 gig connectivity between your leaves and your spines, and then you typically are going to have 10 gig or 1 gig or 100 meg down below the leaves. Off of the leaves, you are going to interconnect any and all kinds of endpoints. Nothing will ever connect to spines except leaves. Spines are basically just the backbone of the fabric. And what we do to connect externally, for example, let's say these are a pair of routers that are going to go off to your MPLS network or your internet or your corporate network, or what else could that be? Data center interconnect. We do that from leaves. Now those are probably going to be 10 gig connections up in here. All right. And if you're familiar with Nexus products, we still do what are known as VPC. So we can actually put these guys into port channels if we want. And we actually support routing protocols at the edge of either OSPF, BGP, IBGP, or eBGP. And even EIGRP is supported at the edge. And then we would call these guys what are known as border leaves. These two switches, leaves 1 and leaves 2, because they interconnect off to some other part of our infrastructure. Right? And we could do that at layer 3 and do routing, or we could do that at layer 2 and we can extend VLANs. So for example, if I was in the midst of a migration, I might actually connect leaves 3 and 4 to the aggregation layer of my existing 3-tier design, and I would make these 802.1q links. And what this would allow me to do is have servers here that are in, let's say server 1 is in VLAN 12. I can have another server over here, server 2, that's also in VLAN 12. So I can extend my VLANs, aka my broadcast domains, my subnets, between these infrastructures by extending a layer 2 connection between them, right? And this is actually often how we do migration. And, you know, you'd probably have your core switches connected to those same routers that go off to the internet and the MPLS cloud and your corporate infrastructure and your data center interconnect, etc. I'm getting a little bit ahead of the presentation here because I didn't mean to be talking about design, but it kind of naturally came up. Does this make sense, everybody? Questions or comments about this? All right, well, let's hone in on this fabric again. So inside of the HCI fabric itself, it's only a layer 3 infrastructure. What is the benefit of having only layer 3, guys? No blocked links at layer 2, right? We've been trying to eliminate this archaic yet invaluable protocol called spanning tree, which has been around for 30 plus years, which prevents broadcast storms in our layer 2 redundant environments. But in a data center, having blocked links is just downright ill-conceived. It's a waste of precious resources, particularly when you're paying premiums for real estate, power, cooling, and essentially high-speed optics for it to be sitting idle doing nothing, which is what spanning tree would render a redundant link. So for years we've been trying to get away from layer 2, and we were almost there in a traditional environment because we were doing layer 3 at the edge. We were doing layer 3 down at the access layer for a minute, and we were doing layer 3 all through the rest of the infrastructure. Layer 3, of course, means you get equal cost multipath routing, which means you're going to be active on all your links, right? Even though there's a little bit more overhead to do with layer 3 routing, there was enough hardware power in our access layer switches 10 years ago, 15 years ago to support this. Does anybody know why we were forced to stick with layer 2 down at the access layer through the aggregation layer in most environments? Why have we been sort of reverted back to layer 2 in most of our data centers? I'll give you a hint. No, switches absolutely can do layer 3. The access layer switches do layer 3, and they have been able to do layer 3 for a decade plus now, and they do it well. They're powerful enough to move high rates of traffic at layer 3. Hint is, it has to do with server virtualization. It has to do with VMware, as well as the other vendors that support server virtualization. Because if you want to vMotion a virtual machine between different hosts, that VM is going to remain in the same subnet, right? We're not going to change the IP of the VM just because it moves to a different host. That would mess up our clients, right? That would screw up our DNS. When you have a client in your corporate environment accessing some service on a server, he or she is using essentially the IP address of that service. So if we move that operating system which houses that service between physical hosts, which is what we do all the time with VMware, you got to keep the same IP address, which means it's going to be in the same subnet, which means it's going to be in the same VLAN, which means you have to extend VLANs in your data center between servers, which means you need to have at least a layer 2, layer 3 boundary at the aggregation layer. So you would typically put your SDIs up on your aggregation layer switches, but everything below that would be layer 2. And this way, server 1 and server 2 can be in the same subnet. This creates a whole bunch of additional broadcast and unknown unicast traffic in our layer 2 domains, which is a challenge. And again, we also have to run spanning tree, which means we're going to end up with blocked links, which means we'll probably have to set up 2 MST groups for spanning tree and have a route on aggregation switch 1 and another route on aggregation switch 2, and then we have to deal with spanning tree issues and blah, 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 blah. It's such a really old-fashioned kind of approach today to have to deal with those issues in a traditional design. So ACI from the ground up is layer 3. Okay? That means that there is equal cost multipath routing going on inside the fabric behind the scenes. You don't even configure it. You don't set it up. We actually use the ISIS protocol to advertise what are known as VTEP addresses. Now, VTEP brings up a whole new topic, which is VXLAN. Okay? And VXLAN is a new standard, it's an open standard way of tunneling layer 2 or layer 3 traffic through this ACI fabric, enabling reachability between any endpoints on this fabric to any other endpoint on the fabric, regardless of subnet. Now, if you guys think about where we've come from, the way that VLANs are supported on trunk links has to do with a protocol called 802.1q. That Ethernet protocol, 802.1q, writes an additional tag to the Ethernet frame. So if you have an Ethernet frame, you've got a destination address, a source address, and a type field. And then there was the payload, right? Payload is probably IP. And the type field is, I think, 0800 or 8100, and that basically means that the payload is IP. When we came out with VLANs and VLAN trunking in an open format, we had to add a field to the header. It made the Ethernet frame a little bit bigger. It's called the 802.1q header. And inside of it, there's a bunch of other fields. One of them is called the VLAN field. And it allows us to mark the VLAN that this Ethernet traffic belongs inside of. And that VLAN field is 12 bits. And 2 to the 12 is 4096. So we are limited to 4096 unique values to isolate traffic from one broadcast domain to another. That supports most enterprises. But in the data center, particularly if you're a public cloud or managed services provider, 4,000 separation domains, not going to cut it. You probably have 20,000 customers. 4,000 different isolation domains is not going to make for a secure, non-leaking data environment. So, VXLAN is actually a layer 3 IP packet. It's not a layer 2 Ethernet frame. It's a layer 3 IP packet. So it's a traditional IP packet in the sense that it has a destination address and a source address. And it has a protocol field and all of the other fields that you find in the header. And then, in addition, there's something called the VNID, or the VXLAN Network ID. This is a unique identifier that allows us to separate out traffic. It's kind of like a VPN in a sense. It allows us to uniquely create flows of traffic separate from one another, just like a VLAN tag did. Difference is that this field is 24-bit, which means we get 16,777,216 unique values. So in a more modern data center environment, we now have almost 17 million isolation domains. That in and of itself is a standard for VXLAN. It's not Cisco proprietary, and many different vendors have de facto moved to VXLAN. VMware uses it, Juniper uses it, everybody uses it, everybody now supports it in hardware. It does add an additional layer of processing, which is done in hardware, but VXLAN is now the open standard. If you have any experience working with OTV or Fabric Path or Lisp, those 3 different technologies have led to this. Now, Lisp is an open standard, but it was created by Cisco. OTV is Cisco proprietary. Fabric Path is Cisco proprietary. Trill was the open standard equivalent of Fabric Path. All of that stuff is really moot at this point. We don't need it because we have VXLAN, and VXLAN is not an additional license. It's built into most Cisco equipment these days, and it's what we use inside the core of ACI. So what will happen is that as these switches come online, the APIC will actually give each one of these guys an IP address. That IP address comes from a pool that we call the VTEP address pool. VTEP stands for Virtual Tunnel Endpoint. Now, Virtual Tunnel Endpoint it's just an IP address. Again, let's say we created a pool of 192.168.5.0/24. The APIC will give each one of these switches an IP address from that range, 192.168.5.1, .2, .3, .4, .5, .6. And by the way, those are /32s, which means they're host routes. So each one of these switches now has an IP address. This is not for management. This is for VXLAN tunneling. And now what will happen is that ISIX protocol I mentioned earlier, which is running here inside the core, is used to advertise only the VTEP address. So each one of these leaves is going to have a routing table which gives it perspective on how to reach each and every one of the VTEP IP addresses of all the other leaves and spines in the fabric. So from leaf 4's perspective, it's .3, but to reach .2, it goes out that interface. And to reach .1, it goes out this other interface. And to reach .4, it goes out this interface. And to reach, and so on and so forth, okay? And there's a routing table that basically just informs reachability of the other VTEP addresses on the fabric. Once you can ping from any leaf to any other leaf or spine, or I should say any Nexus ACI enabled device to any other Nexus ACI enabled device on this ACI fabric, once you have that, now reachability between the endpoints becomes easy, because at the edge, what we're going to do is we're going to encapsulate our traffic into what are known as VXLAN tunnels. Whoops. So let's say here's server 1 and here's server 2. And remember, I put IP addresses here of 192.168.5.1/32.2. You know what? I should have done it this way. Let me do it like this. 192.168.5.1, .2, .3, .4, .5, Those are the VTEP addresses, virtual tunnel endpoint. And now let's say this endpoint is in the 172.168.10 subnet. Okay? These two guys, server 1 and server 2, they're in the same VLAN. They're in the same subnet. When they communicate to each other, they do so at layer 2. Server 1 generates an Ethernet frame for server 2's address. When that Ethernet frame comes in on leaf 1 throws it into a VXLAN packet. Remember, this is an IP packet with the destination IP address of 192.168.5.3, which is leaf 3. And that packet is routed through the fabric, and when it gets to leaf 3 receives it, and then it strips off the outer VXLAN packet, and it delivers the initial Ethernet frame to server 2. So we're able to carry layer 2 traffic over this layer 3 fabric, okay? Just like Fabric Path did, just like OTV does. We encapsulate and tunnel layer 2 traffic over the ACI fabric. Similarly, even if these guys were on different subnets, check this out. Server 1 and server 2, let's put them on different subnets. So we got 172.16.10.1 on the left. And let's say that guy is going to use .254 as its gateway. What will happen is that leaf 1 will become the .254 gateway on that 172.16.10 subnet. And then let's say server 2 is in the 10.10.10.0 subnet, and its gateway is going to be 10.10.10.254. Similarly, this guy is going to become 10.10.254. So the leaf will become the gateway that's required for inter-VLAN routing or layer 3 routing. And now you know that when server 1 is trying to talk to server 2, there is an IP packet which goes into an Ethernet frame. Basic switching and routing, server 1 is going to do an ARP for its default gateway. The leaf is going to respond back with its MAC address, and that Ethernet frame comes in on leaf 1, pointing to leaf 1's MAC. Leaf 1 then strips off the Ethernet header. It reads the destination IP address. It figures out where this packet is going, and then it, once again, encapsulates it into a VXLAN packet with the destination of 192.168.5.3, throws it into a tunnel, and that packet arrives on leaf 3. Leaf 3 decapsulates the VXLAN header, sees the initial IP header, and then is able to route that to server 2 at layer 3. So whether it's layer 2 or layer 3, anything is reachable on the ACI fabric, and there's no spanning tree ever running inside the fabric because it's actually designed as a layer 3 core. So VXLAN will become the standard in our data centers. It's already built into ACI, and there are some really creative and innovative ways that we actually use it between ACI fabrics now in different data centers. So we can actually extend the VXLAN capabilities outside of the ACI fabric, and we can build large-scale ACI fabrics that are managed by a single pair or a single cluster of APICs. Remember, the APIC controllers, and I didn't actually mention this, but our APIC controllers come in a minimum of 3. So you're going to have APIC 1, you'll dual connect it, you'll have APIC 2, you'll dual connect it, and then you'll have APIC 3, and you'll dual connect it. And those 3 APICs operate as a cluster. They're also connected out of band to each other. So what I haven't demoed yet on this diagram, I'm going to add it in now, is that your APICs, which again are your controllers, they dual connect to the fabric. Say this is A2, and here's A3. We'll just distribute them across the leaves. And they themselves are connected to an out-of-band management network, which is also where, in all likelihood, your management device, right, your laptop, your desktop, whatever it is, that you're then going to be using IP to connect to the IP address of your APIC. And each APIC has its own IP for management. They're active, active, active. They are active in a cluster that's not a standby active relationship. You can actually connect to any one of the APICs, and they have a sharded database. And if you change a config on any APIC, it updates it on all the other APICs. There's ultra high availability. There's 3 APICs just in case you have more than one failure. A single APIC can support the entire fabric. Now, if you lose all 3 APICs, your fabric is still going to operate. You're just not going to be able to make any changes to it. So, let's see, what's next? Yes. The real strength and strengths of ACI, which has to do with these policy databases that I was mentioning. Now, this brings up another topic called endpoint groups. An endpoint group can be defined by a number of different characteristics. It's essentially a common denominator for categorizing our services. So you might say all servers that are providing web. You might say all servers that are in a specific VLAN, all servers that are running a specific operating system. Whatever you want, you can define the endpoint group based on 6 or 7 different characteristics, including VM attributes. And it would be metaphorically similar to me saying, okay, everybody who's wearing a shirt today is in endpoint group X. And everybody who's wearing a bow tie is in endpoint group Y. And everybody who has brown hair and a bow tie is in endpoint group Z. So I've got a lot of granular control over what characteristics or attributes will cause a device to end up in an endpoint group. All right, and once a device is in the endpoint group, let's say server 1 and server 2 end up in the endpoint group web, right? We might have other endpoint groups, let's say database, and I put server 3 in there. Here's server 3. And by default, only servers within the same endpoint group will have any communication. No data is ever allowed to flow on the ACI fabric unless endpoint groups are established. And then only data within traffic within the same endpoint group is going to be permitted to flow. If you want to have, let's say, your web servers talk to a database server, you have to explicitly create something known as a contract. And that contract will contain specific port information, as granular as you'd like to go, source and destination port, thereby controlling the application. So you can say that my web servers are only ever allowed to talk to my database servers on port 6002. And then the database server is allowed to respond back to the web servers on whatever the generated source port was. But other than that, nothing else will flow, right? And you can do this with multiple, group. You could say, okay, my database servers also have storage connectivity, and that runs on a different set of ports, and that's another contract. And together, this thing is called an application network profile. It's all of the contracts between the endpoint groups that you establish for a specific set of services. And you can have hundreds of application network profiles, each doing different things. These application network profiles, you guys, are stored in the policy database on the APIC. The cool thing is, as the server team deploys services on Fabric, you don't need to go and create new QoS policies, new access list entries, new VLANs. It's all automated. You create the endpoint group up front. It uses a pool of VLANs that you set at the start of the deployment, and it grabs the VLAN that's available out of the VLAN pool. It programs all of the leaf switches that require it, and no matter where that service moves, let's say it's your web servers are virtual. That means you can have a VM on server 1, you can move it over to server 2, and wherever that VM goes, so will the policy be enforced. Questions or comments? This is actually quite radical, guys. Think about this. Efficient use of resources, hardware tables on the leaves. Policy is only pushed to leaves as needed. If there's a virtual machine or a bare metal server of some type that is in an endpoint group, the leaf will then download the policy, including whether or not it needs to be the gateway for that set of users. If not, we don't instantiate those requirements on any leaves, thereby conserving resources and hardware on those leaves. When you stand up a new service, all you have to do inside the APIC is create a new EPG for it. Everything else is automated. You don't go program your switches any longer. And in fact, this kind of leads us to the next subject. But if you have VMware in the environment, okay, let me redraw this actually in another separate piece here. I'm just going to draw in 2 leaves just to speed up my drawing process. If I have, let's say these are ESX hosts, that's ESX1, and here's ESX2 and ESX3, okay, and they're in a cluster together, and then here's my vCenter server, right? Here's my APIC. My APIC is connected at a band. My APIC talks to my vCenter server at a band. My APIC actually pushes a virtual distributed switch through vCenter. If you guys are familiar with the Nexus 1000V, this is similar to that. The APIC actually controls the VMware VDS in the VMware environment by synchronizing or integrating to vCenter. And then when you create an EPG, let's say it's EPG blue, it automatically instantiates an endpoint group, or the equivalent in VMware, which is called a port group, and a VLAN onto that virtual distributed switch. Your vCenter administrators are no longer doing networking. They are going to deploy a VM into that port group, but they don't create the port group and they don't create the VLAN. That's all done here on the APIC. If they remove all VMs from Endpoint Group Blue, then leaves 1 and 2 don't need to download the policy for that particular endpoint group. So you no longer have to worry about cleaning up config changes just because the server team decided to abandon a particular service, right? And if they forget to tell you about it, instead of leaving, multi-year entries that are consuming resources in my access lists and VLANs that no longer are being used and such, it disappears from the fabric. Now, it does remain inside your policy database. You may want to clean up your policy database from time to time, but otherwise it's doing no harm on the fabric in terms of consuming resources. And once you establish your endpoint groups, here's endpoint group green, and then you create a contract between the two of them, and you build what's known as an application network profile, you don't really have to keep track of what the server team is doing. If they deploy VMs that belong in either one of those endpoint groups, they'll automatically get the policies. Do you see the operational benefit of this, folks? Okay, Joe has written a question. This is exactly the config we have. Has VMware decided this config is now supported? Our last conversation with VMware states that the creation of the VDS by the APIC is not supported. No, it's absolutely positively supported in 5.0, in 5.1, in 5.5, and for the past year it's been supported in 6.0. So I guarantee you I've done multiple deployments with both versions, including the latest version of VMware, and that is supported, yes. Now, in addition to this, in addition to the hypervisor integration and then the application network profiles that we build, we can also deploy appliances on the fabric. So let's say you might want to throw in a firewall, or you might want to throw in a load balancer, okay? The APIC will be programmed to be aware of where that firewall and load balancer are on the fabric at any time. And when you have your EPGs, let's say the EPG web talks to EPG app, talks to EPG database, 3-tier application. That contract can also contain QoS policy, and it can also redirect the flow of traffic between, let's say we want to go to a load balancer, or we want to go to a firewall. We can actually redirect the flow of traffic anytime, anywhere. So if you move a VM, you can still rest assured that even though you've moved that VM to a different physical host, the flow of traffic will still be forced through whatever service graph you instantiate in the application network profile. So if you say, I want the traffic between web and app to go to a load balancer, even if you move your VMs around, even if you move your load balancer around, assuming it's a VM, because it can be, the APIC will ensure the redirection of traffic using VXLAN through that specific appliance. Another very strong operational benefit and feature to ACI. All right. So currently there's dozens of popular appliances like F5, A10, Cisco ACI firewall, Citrix load balancer, Checkpoint, et cetera, that are all supported in the ACI fabric for integration. There's also what we call a Northbound API, which means that the APIC is programmable via what's known as a REST interface. So REST is just basically a fancy use of HTTP. And it's just a way of delivering scripting to the APIC. So I can actually set up, for example, my laptop I download Google Chrome. I get this application called Postman. All right, it has a RESTful client, and then I connect to my APIC, not in the GUI, but I connect via what's known as an API, or an application programming interface, and then I'm able to push either XML or JSON scripts, and I configure the APIC remotely using XML or JSON. So if I know that I want to create an application network profile, I have a little script on my machine. I customize it for the new application network profile, but then I just push it in. Instead of having to take 6 minutes on the GUI, it takes 6 seconds using Postman. And you can do everything to configure the fabric using XML or JSON. There's even a Python interpreter that runs on the APIC if you want to actually run Python code to further develop custom applications that would allow you to, let's say, automate your environment. Right? This is all about being able to automate the management of and troubleshooting of your environment. Now, this is actually a Northbound API because it's programming the APIC, even though I drew the laptop down below. And that's because other products like vCloud Director, which is VMware, or OpenStack, which is, of course, an open standard, and things like Puppet or Chef, these applications all have what's known as a RESTful API, and they too can program the APIC using XML or JSON code. So as long as those Northbound applications themselves have a RESTful API, you don't even need to log into the APIC directly. You can actually do all of your configuration through, for example, OpenStack. There's actually a plugin in OpenStack that allows you to create application network profiles in OpenStack that are then translated through the RESTful interface to the APIC via either XML or JSON. So there's an enormous scripting and automation and orchestration potential built into ACI as well. All right, now if I go back to this diagram that I initially drew up here, okay, where I had my old data center infrastructure and my new ACI fabric side by side. See how both fabrics are connected to these routers that go out to the internet here, right? So I got layer 3 routing from both fabrics out to the internet. And I'm running layer 3 routing from those internet routers here to ACI using either OSPF or iBGP in most cases. Right? So I'm able to advertise between my ACI fabric and those external routers, and conversely learn the outside routes. Now we don't ever run BGP on our leaves, internet BGP. We can run iBGP or eBGP from an interior gateway standpoint, but we don't do internet routing on our leaves, so we still need internet routers in the data center. All right, but we can, of course, exchange routes, and then I also drew in these layer 2 connections between leaves 3 and 4 that are these 802.1q trunks, which means that I can actually now have servers, like here's server 1 and server 2, and then server 3, they can all be in the same VLAN. Traffic would need to flow, of course, from server 1 over those trunk links to the ACI fabric, but those can actually be in the same broadcast domain. Now, what does this mean for you? It means that if you have a virtualized server environment, and these happen to be ESX hosts, right? ESX1, ESX2, and let's throw a vCenter in here because we're going to need it, and ESX3, okay? We can still, because remember the APIC is talking out of band to vCenter, and vCenter is probably talking out of band to its ESX hosts. There are 3 APIC controllers. There's extra high availability on the APICs. And even if you lose all of your APICs, your fabric still continues to pass traffic based on its last known state. So it doesn't kill the fabric if you lose all 3 APICs, but you're not ever going to lose all 3 APICs unless you have a total power outage, which means your infrastructure is down anyway. Yeah. So, but your APIC is configured to talk to vCenter, and remember I said earlier it's going to push that V switch, right? So there's going to be a virtual distributed switch that runs across that cluster because it's defined as a data center in vCenter. And so the VDS runs across that cluster, and then look what you can do. You can actually have a VM that's physically associated with, let's say, ESX host 2 on my old data center environment. You can vMotion it over to ESX 3, which is on my ACI fabric, without the clients even knowing it. Now, I would never really do this without a maintenance window, but it's completely doable, right? So this is how we migrate our virtual workloads. Typically, we set up the VDS to span both fabrics. We move all of our VMs over, and then once those are moved over, we decommission the servers from the old fabric, and we reconnect them to the new ACI fabric. And then we actually put the gateway locally on the leaves for those VMs, and we convert what's known as the bridge domain over to a layer 3 bridge domain for those subnets. Prior to that, we needed to actually keep the gateway on the aggregation layer switches because that's where the SVIs were defined. And the VMs that we move over to our new fabric are still going to be using the SVIs on the old fabric. Until we get all our VMs moved over, we decommission those servers like I mentioned, and then we physically relocate them on the ACI fabric, and then we enable layer 3 for that bridge domain, and that means that the leaves will instantiate gateways as needed per subnet. This can be a lot of information all at once, folks, which is part of the reason why we're presenting this seminar to you, this webinar, I should say, because if you're interested in learning more, we would like you to come to one of our classes to learn more, right? And if you do come to one of Sunset's classes on ACI, we'll go into great detail on any and all of these topics that I've covered today. So we'll actually study them in much greater detail, but then we'll also have hands-on labs that correlate to all of these different features: hypervisor integration, layer 3 routing, layer 2 extension, EPGs, application network profiles, so on and so forth. Question from Matt: what happens when you have multiple vCenters for large organizations? The APIC can push as many DVSs into as many data centers, into as many vCenters as you need. Certainly there's some upper limit, but I don't think that we're going to hit it in most cases. So there's no limit on how many DVSs the APIC, there is a limit, but there is some very high limit on the number of DVSs that the APIC can manage. And the APIC can talk to lots and lots of different vCenters. It's not limited to talking to one vCenter. When you set this up in the APIC, you actually specify different vCenter domains. Other questions or comments, guys?
Hey, can you hear me?
Yes.
This may be a dumb question, but if I had multiple EPGs, let's say 2, could I have the hosts on the same subnet and not have them communicate without contracts? Does that make sense?
That's a very, very interesting question. Who is speaking?
Tony.
Tony, what you're referring to is actually called microsegmentation.
Okay.
Right? So this is a new phenomenon in our data centers because when one of our servers is compromised in a layer 2 broadcast domain, it usually means that the hacker has some type of layer 2 connectivity to all the other servers in the same VLAN. Because the hacker, as long as the hacker can falsify and spoof layer 2 broadcast traffic, he or she has reachability to then find vulnerabilities in other servers in the same VLAN. So what has been up and coming in recent years is something called microsegmentation, which means that even though servers are in the same subnet, in the same VLAN in the data center, it's kind of like private VLANs, if you know how those work, where devices can't communicate to each other even though they're in the same VLAN. And we accomplish that with firewalls, typically. Or if you're using something like the VMware Virtual Distributed Switch, you can do it. Or if you're using the Nexus 1000D, you can do it. So microsegmentation is now built into ACI. So you can do it at the leaf level. So you can define an EPG, and you can actually say, I want this EPG to be microsegmented, which means the devices in the EPG will only have access to their gateway. They won't be able to communicate at the broadcast level to any of the other servers that are in the same EPG. So yeah, you can do that with ACI.
Got it. Thank you.
You're welcome. All right, well, I can say this. Everybody's going to go to SDN. There isn't a data center on the planet that isn't eventually going to go to some type of software-defined networking. It just makes, there's just too much of a cost benefit. It's sort of like when we had voice over IP. You know, how many organizations still have old school PBXs? 1%, right? Because it's just too compelling of a cost savings. Now, what's the cost savings here? Obviously, you have to invest in a new infrastructure. People are not thrilled about that, especially if they bought into the whole Nexus 7000, 5000, 2000 model 8 years ago with Cisco. But once you get past the initial capital investment for the infrastructure, which, by the way, is cheaper than traditional Nexus switches, then where you're going to actually make your money back, where the ROI is in the time consumed by engineers manually standing up services and enforcing security and quality of service policies on a traditional infrastructure. So it's really a manpower gain that you're obtaining when you move to ACI. Also, again, due to automation, configuration becomes really, really simple. Now, troubleshooting is still complex. You still have lots of job security. It's not like you're going to be pushed out of the organization just because there's ACI, you need less engineers. No, it's not true. We need better engineers who understand not only routing and switching, but SDN and scripting. So if you want to really stay relevant in your careers, I implore you to really learn about these new SDN paradigms and to study things like Python or XML and JSON scripting, which are becoming the de facto standards in most environments, XML for sure. Okay, I've got some questions on the screen from Placido. Can you share VMW integration, then talk layer 4 to 7 integration with F5? I think I covered VMware integration already, right? The APIC is configured to talk to vCenter. The APIC gains certain privileges in vCenter, right? You've got to set this up in the APIC. You also have to set up a user account in vCenter if you don't want to give the APIC admin privileges. And then the APIC is able to actually deploy a VDS across the hosts in a specific VMware data center. And then when you create EPGs on the APIC, they're automatically translated. A VLAN is selected from a dynamic VLAN pool, and automatically the EPG is translated into a port group on the VDS so that the VMware administrator simply deploys the VM within a port group and no longer does the networking function. Now, if you're talking about full integration with an appliance like an F5, which I strongly recommend against, that's different than just locating the F5 on the environment. If you want the APIC to be aware of where the F5 is, and then you want traffic to flow to the F5, you simply do that with, you create a service graph in the APIC that tells it where the F5 is, and then you use contracts in your application network profile to redirect traffic through the load balancer or through any appliance that you've defined. And that's actually the best way to go. It's called network stitched mode. And that is the mode we recommend to our customers. There is an additional function that we've deployed, I've deployed personally, which in the end nobody ever goes with, and that's full integration with F5. That means that the APIC can configure the F5 load balancing function. Now, why in the world would you want to use the APIC, which is clunky compared to the F5 GUI, to manage the F5s? It doesn't actually really make sense. It's totally doable, but then you get into very granular controls and odd techniques inside the APIC to program, and I mean like literally set up and configure and set policies for some third-party device. That third-party device probably has a far greater management platform. Now, you might argue and say, well, I want a single point of configuration. Fine, go to town. Use the APIC to configure your firewalls and your load balancers, but you're going to have engineers dedicated to learning how to do that from inside the APIC. Now, here's the deal. Sunset is a learning partner of Cisco. Their business is education. So we're doing this webinar because we're trying to show you guys that there's some value in attending ACI training. And I can assure you, because I've taught these classes dozens, maybe even hundreds of times, if you come to the 5-day training, it's totally comprehensive. It does everything from fabric initialization, initially, meshing in the nodes, basic APIC configuration, that straight out of the box, what you need to do to get your fabric up and running, creating tenants, working with VRFs, creating your access policies for the equipment that's going to connect to your fabric, setting up your application network profiles, doing bare metal servers, doing virtual machines, integrating with the hypervisor, and then setting up layer 3 external routing, setting up layer 2 extension of our EPGs so that you can do migration, for example, and then even integrating an ASA firewall, full integration, not just network stitched mode, although that'll be covered. Plus all sorts of management, how to create users, how to set up SNMP, how to do monitoring, how to do troubleshooting. That's in the comprehensive 5-day class. If you can't leave the office for more than, let's say, 3 days, you might want to take a look at one of the other 2 options, which is your ACI Field Engineer Essentials course. That's only 3 days. That covers all of the initialization of the fabric, the setting up of the tenants, the policies, the layer 3 routing, the layer 2 outs, and your integration of appliances. Your operations and troubleshooting bootcamp is 3 days. That's more focused on day 2 operations. So you have everything up and running, but now we need to actually monitor. We want to do syslog. We want to do SNMP. We want to use special things called atomic counters. We want to learn some of the special troubleshooting techniques that are available in ACI. That course is more for you, day 2 operations. Does the 5-day course cover scripting, use of Postman? It does. We don't actually teach you scripting, but we do use Postman to both push a Python program and XML scripts to the APIC so that you see how that works. And I think the other 2 courses probably contain it as well. I can double check for you. In fact, probably the best thing to do if you're interested in any of these 3 courses is to contact your Sunset Learning salesperson, the person who signed you up for this course, and they can help you to navigate which course may be right for you if in fact that's the direction that you're headed. Any other questions or comments, ladies and gentlemen, on any of this stuff?
All right, if there's no more questions, we can go ahead and wrap this up. Thank you everyone for joining us. If you do have any other questions, like you said, just feel free to reach out to me or one of your reps and we can answer more questions for you on training. Also, we did record this, so I'll be sending it out probably sometime next week in case you missed anything. So everyone have a great day and thanks for joining.
Thank you all. Thank you, Kristen. Thank you everybody for attending.